Hi, welcome to EC&M Tech Talks. This is a series of how-to videos where we cover everything from maybe a little basic theory on into the equipment itself and how some of it operates, and importantly, how we need to install it and maintain it. So that means we need to talk about the various codes and standards that exist for our electrical equipment as well. I'm Randy Barnett, your facilitator for today in these particular series of EC&M Tech Talks then. If you haven't already, you need to go to ecmweb.com, Electrical Construction and Maintenance Magazine. So go to ecmweb.com, and in the upper left-hand corner, you can click, there's a premium content. When you hit the drop-down box, there's a premium content is the very first item you'll run into. Go ahead and click on premium content, and if you haven't already, sign up for that premium content. It's free, and you'll have access to tons of information, everything to do in the world of electrical construction and maintenance, especially what we're going to be talking about today, which is bonding. Bonding for safety and compliance. That's where we're headed. So what we want to do is we want to talk a little bit about what bonding is and different ways that we can accomplish bonding. We want to look at the definitions in the National Electrical Code. We want to look at some practical things that are going on, like behind me in this panel board. And then we want to talk about Part 5 of Article 250. Article 250 is, of course, on grounding and bonding, and Part 5 is just bonding. So we'll do an overview of Part 5 then after we look at a couple other things. Okay? So if I take and I join something together, I don't care what it is. If I just take, two pieces of wood and glue them together, I suppose I bonded that wood, those pieces of wood to each other then. And the same is true when it comes to electrical equipment, right? If I take two pieces of metal, metal components, and I take and I somehow bolt them together, I have bonded them together. Of course, I'm usually not going to do that, right? I'm going to take something like maybe a piece of wire, specifically with some probably green insulation on it, or the code tells me it could be green with one or more yellow stripes, or it could be bare copper. And this is called my equipment grounding conductor. And I can attach this to the inside of my box, like we're going to see behind me here in a couple minutes. And then I have bonded to this particular box. Now, let's go back to Article 100 in the definitions of the National Electrical Code and look at some of this terminology then there, because there are several definitions that relate to bonding. Now, by the way, I'm using the 2023, of course, National Electrical Code. And as you know, the 2023, well, in case you don't know, now you'll know, the 2023, they've taken all of the definitions that appear elsewhere throughout the code, usually in 250.2 or whatever it was, that .2 section, and they move everything up to Article 100. So we find all of our definitions now in Article 100, which is going to be convenient for us, and they don't divide it up anymore into Part 1, Part 2 over 1,000 volts, and so on. It's all just simply in alphabetical order. So all we've got to do is find bonding, bonded in the Article 100, and we'll see what it has to say. So I look up, let's see, there's a total in relationship to bonding. There's 1, 2, 3, 4, 5, 6 different definitions. And bonding, connected to establish electrical continuity and conductivity. So that's what we're doing. We need to create an electrically conductive path, which of course we can do with a piece of wire, and attach that to a box, and then we would have a complete path back to the source is where we're going to find out where we're going to head. So definition for bonding, and it's simply some way to establish conductivity. Now, I don't have to use a piece of green wire. I have different pieces of conduit. For instance, here's some electrical metallic tubing, and so it will carry current flow. If I were to take my multimeter back here and read the resistance on it, I'm sure it's right at 0, okay? And so I can use this to carry fault current. In fact, Article 250 is going to list all of the different types of conduits, raceways, and so forth that I can use for my equipment grounding conductor. Now, the thing we have to be careful about is when we take and we put something like this coupling, we have to make sure that we get the set screws tight on our coupling. If not, if I've got a loose connection, I don't have good electrical continuity, do I? The same thing is true. I have to be really careful when I use something like rigid conduit. rigid conduit. I have NPT threads and they're tapered, so they're tapered down. And then I take galvanized rigid conduit is what this is. This is a nipple, right? Less than 24 inches. But anyway, I take and then I put a coupling on it, and the coupling has straight threads on the inside. So if I put those straight threads on some tapered threads, they're going to be loose unless I tighten that coupling up and our connector, whatever it is, I tighten it up and get it wrench tight, right? Now, things like wrench tight are not defined in the National Electrical Code there, though that term is used. What you need to do, if you need to know any of the specifics about, for instance, how to thread conduit, how many threads you should have, and how tight you should get your fittings and so forth, take a look at the National Electrical Installation Standards from NECA. They are ANSI-approved standards, the National Electrical Installation Standards. We talked about them before here in these tech talks, and that's what's going to help you to figure out how to thread your conduit and how to make it wrench tight and all of those type things in. Okay, so take a look at those NEIS standards. Right? So that's what bonding does for us. It joins metal together with metal. Now, a couple of the other definitions. There's a bonding conductor. There's a definition for a bonding jumper, which I've got a bonding jumper installed back here, and I can take this bonding jumper, it's connected to the box on one end, and then I can take and connect it to my receptacle that's mounted inside of this cover. I can connect it to the equipment grounding conductor that's coming in from my panel board, or I can connect it to equipment grounding conductors going elsewhere. I can connect them all together, because what I want to do is I want to create that electrically conductive path then to create what 250.4 calls an effective ground fault current path. So we'll talk a little bit about that as well. Anyway, other definitions I have: bonding jumper supply side and bonding jumper system bonding jumpers, and I also have a definition for a main bonding jumper. So let's talk about those a little bit. So first, our main bonding jumper. Our main bonding jumper is only found in the service panel. In other words, that first panel right after the supply from the utility for our service. And so I have a green screw up here. That's my main bonding jumper. One of the things we have to do is anytime we're going to use bonding jumpers, we have to size them properly. Table 250.122 is going to tell us how to size our bonding jumpers based on the size of the overcurrent protector device back here. So we'll talk a little bit about that as well. Now, as far as the screw, we don't size the screw. It comes from the manufacturer, it's UL listed, whatever it is, and that's what we use for our main bonding jumper. The system bonding jumper, if this were not the main panel from the service, if this were a sub-panel somewhere further downstream, part of a separately derived system, that particular bonding jumper in that separately derived system, I would call that a system bonding jumper then. Same function, size it, same way, and so on. But anyway, a little difference in terminology there. Now, 250.4 tells me why I bond, why I ground as well. But the reason that I bond, it says, is to establish an effective ground fault current path. So what the heck is that talking about? Well, let's take this receptacle. So I've got a receptacle mounted in my cover, and I've got the ungrounded black conductor going to the ungrounded side of the receptacle, the narrow slot as I call it, right? And then I have the white conductor, which is our grounded conductor, or the neutral as well in this case, and it goes to the neutral side of my receptacle. I haven't yet connected any of these green wires to my receptacle. Now there are some options for me depending on what I'm doing, and we can talk about that. But I have to size. So what I've got is running from, in this case, what is a 15 amp breaker. So I go from a 15 amp breaker. I come off with some, in this case, some number 14 MC cable. So I use type MC metal clad cable, and I supply this 4 square box with it. I have connectors at each end that give me good, they're listed connectors, and those connectors give me good bonding to those enclosures then. I also have a set screw on there I have to tighten down to make sure that I get that good firm connection. Now, you think about it, if there's any current that leaks into the frame of this enclosure, whether it's the cover or the box or whatever it is, I need to carry that current back to the source so that I can trip this circuit breaker. And so to do that, I need for current to travel on this green equipment grounding conductor, which we use for bonding. Okay? Carry current back to the source, back to the neutral bus bar, where it'll go back on the white grounded conductor wire, right, our neutral conductor, all the way back to the transformer. Once I establish that complete path for current flow, then, if I have enough current flow, as I would expect to have in a ground fault, definition for ground fault, where current flows into the metal components of our system that don't normally carry current flow. So if I have a ground fault, I want this breaker to trip, and that's what will happen. Current flow will flow along the green wire into the neutral bus bar, back up to the transformer, and my breaker trips and clears the fault for me. Now, it says in 250.4 I have to have an effective ground fault current path. And what that means is, in a DC system, we would talk about, well, along that equipment grounding conductor and back to the source, we'd have to have low resistance. I can find the resistance for any size conductor that we use in the NEC. I can go back to the tables in Chapter 9, and we can find the resistance in ohms per 1,000 feet of a given size copper conductor. However, it doesn't give us the impedance value, really, does it? So impedance, remember, I've got to go back to basic theory. Now, in an AC system, we have more components than just resistance as opposition to current flow. Because of the magnetic fields and the capacitive effects on the conductor, we have to take those into account when we calculate impedance. So impedance is the total opposition to current flow in an AC circuit. So that means, practical side, if I had a whole bunch of equipment grounding conductor out here that I was running, pulling through a conduit or something, I wouldn't take and just, wind it all up and stuff it inside of a box somewhere. I don't want a lot of bins in my equipment grounding conductor any more than necessary, certainly. And I certainly don't want to coil it up, because that's going to just create a lot more inductive reactance in my circuit and limit the current flow back to the source. And when I have a ground fault, I don't want to limit the current flow. I want the maximum amount of current to flow in that short period of time then. Now, a couple of different options as to how I mount this. When it comes to a metal box, if I'm going to put in, let's say I'm going to mount it on a surface, okay? If I'm going to mount this metal box on the surface, as I typically would with something like this, and I'm going to put a receptacle inside of it, then how do I bond this receptacle to that metal box? I could run a jumper wire, an equipment bonding jumper then, from the metal box to my receptacle, and you'd probably use a wire nut and also attach it to my equipment grounding conductor coming into the box. But it gives me some provisions in 250.146. 250.146 says if this is going to be a surface-mounted box and I need to mount a device in it, I can pull off one of these paper washers from the back side of my receptacle. I pull off the paper washer, and now I can get good physical contact and actually bond the yoke of this receptacle to the metal on the in the box. Get a good low effective or a good effective ground fault current path through that. Also, something else, now I can't do that if I'm going to mount this box flush. If I were going to mount a metal box flush, and I either have to install the bonding jumper, or I could use a receptacle like this. This is a 20 amp receptacle, and it's got a little spring clip on one end of the yoke. And that little brass spring clip, I could use this in a flush mounted box, put this in there, tighten it down, and still get good bonding to the box. So I'm allowed in 250.146 to do that. So that's a little bit on bonding itself. Now, some things, like PVC conduit and non-metallic boxes, I got to run the equipment grounding conductor, right? This is not going to establish any conductivity for me. And so, for example, here's some fiberglass conduit, and certainly it's not going to provide me an equipment grounding conductor as well either. Now, and so Article 250, bonding. Well, it talks about one of the first things in 250.92, it talks about our service. So think about our service. I could have a large amount of available fault current. because this is my main breaker. This is my first overcurrent protection after the transformer from the utility. So these conductors coming in could carry a considerable amount of available fault current. And if that current leaks into the frame of my enclosure, I still need to get it back to the transformer, don't I? Now, in order to do that, 250.92 says, look, you can't just use a regular old lock nut up here at the top and bring that service in. So for instance, I've got a threaded hub up here. I've got a grounding or bonding bushing that has a set screw that goes in and makes contact with, when you tighten it down, it makes contact with that hub. And then I've got a lay-in supply side bonding jumper running there as well. All to increase that conductivity, make sure I have a good low effective ground fault current path all the way back to the source. It's also the same section 250.97, which is for bonding over 250 volts to ground. So if I had a 480-277 system, it's going to refer me actually back to 250.92 and say use some of those same methods that you use at the service in order to bond these 480-277 or 600-347 systems to ground, whatever you've got. 250.94 talks about communication systems in Part 5. Now, two different systems. We have our electrical distribution system and we have our communication system, network systems and all of that. I need to bond those two systems together. And where I'm going to do it is right back at the grounding electrode conductor that runs from my service panel to my ground rod. And so here's a device, an intersystem bonding connection device, where I can do my intersystem bonding terminations. So I could bring in my equipment grounding conductors, bonding conductors from my communication system and tie them into this intersystem bonding termination device then. So that's covered in 250.94 in much more detail. 250.96 says you got to bond other enclosures as well, okay? And if you think about it, you go back, what do we have to bond to? Anything that could potentially carry current but normally doesn't. So my metal enclosures, boxes, conduit runs could become energized, and if they do, we need that bonding path all the way back to the source. Now, 250.98 Now 250.98 talks about our loosely jointed metal raceways. And so there, for instance, I think of my expansion joints. I'm going to have to provide proper bonding, use a proper type of expansion fitting, and make sure that I have proper bonding through that expansion fitting then or around it. 250.100 talks about bonding in hazardous locations. You think, oh, that must be really huge. No, not really. It's a fairly short paragraph. And the reason is because it's going to refer you back to Chapter 5, where we covered hazardous classified locations then for proper grounding and bonding. 250.102 gives me a table, how to size my bonding jumpers. And it's always going to be based on the size of my ungrounded phase conductors coming in. That's going to give me and tell me what size grounded conductor I need coming in, as well as what size of any bonding jumpers I'm going to install. And that's table 250.102C1, and it's entitled Grounded Conductor and then Jumpers. The main bonding jumper, system bonding jumper, supply side bonding jumper for alternating current systems. So on the left-hand side of the table, it gives you the size of your ungrounded conductors, and then on the right-hand side of the table, it gives you the size of your bonding jumpers. 250.104 talks about bonding of piping systems, spends a lot of time on metal water piping. So we have things for bonding, for instance, this little clamp. This is for bonding to a water pipe. So I can clamp this around the water pipe, then there's a lay-in lug up here. I can take and run my equipment bonding conductor through there, tighten the set screw down, and have a good solid bond. So anyway, that is Article 250, Part 5, an overview of it. Bonding, why we bond. We bond for safety, to make sure that if metal equipment does become energized, that should not become energized, we have a way to get it de-energized. And that's that effective ground fault current path all the way back to the source till they allow the breaker to trip or the fuse to blow and clear the fault then for us. So, lots of grounding and bonding, huh? We just barely scratched the surface on bonding. Anyway, remember that this Tech Talk is brought to you by EC&M Magazine. They are part of the portfolio of Endeavor Business Publications. And the main thing is that when you go out of here, make sure that you work safely. We'll see you on the next Tech Talk.